Okay, just so you understand, we're using CMOS, complementary metal oxide silicates. These are the sensors that detect individual light photons. This is not unknown. Now, you always hear about light waves. It is a wave or is it a particle? Well, I'm going to tell you it is both. And these are the waves, and that's the particle that pushes forward and creates a separation zone between each wave. There's something else to remember here. These are the neutrinos. They're starting to gain energy as they push against something. Energy is pushing and shoving. These are starting to push back against their own partners up in front. So they're pushing, shoving back, pushing, shoving back. So you end up with these not quite photons. These are the photons. They are being accelerated, and they're going to divide right here as they go through the Venturi, and then you get this big white effect over here. But these are your waves, and these are your particles that create the wave, because it has just a magnetic field around it. And that magnetic field is basically about this big. All right, and this one has one here too. So they keep these, you stay away from me, you stay away from me. That's the separation zone. I'll show you that again. All right, see, these are the pulsations of those particles, and these are the waves. These here, or that are all glowing, these little glowy spots, are particles that are in the air. What particles are they? Well, they can be gases. Gases are all made, everything there is, 100% of everything is made of these little dipole particles, which I just showed you, the black and the white. That's all there is. You make them in bigger and bigger and bigger piles, you end up with bigger and bigger and bigger molecules. But the smallest ones are light, and they still have a lot of push to them. So when they push through all the other particles that are in space, they create this wave and glow, just like a jet fighter does coming through the atmosphere. These have to glow a little bit because they're getting pushed out of the way. And that glows a lot because it has to push a lot of them out of the way. All right, so let's continue on. Don't forget, pulsation, particle in there, separation zone. All right, watch this now. These are the particles. This is where they just start to explode into little bits and pieces. This is that event taking place. These are the little particles glowing more and more and more until they get so excited they literally crush each other into their fields. That's because this is a Venturi. And all the particles have fields like this. Not that big, but they have fields. And they all have to crush each other's fields. Anytime you crush one field to another, it's called a Casimir effect, it creates energy. And energy is luminescence. Luminescence is heat and energy. So what did we do? We accelerated that light. No question it accelerated. If you can't see acceleration, I don't know what you can. That's going, it's just starting to accelerate here. Just starting to, because of the Venturi. And then the Venturi sucks that particle right through. That's what a Venturi does. Just look it up. And when it does, the fields compress so violently that the black can't get through. It's because of the design of the Venturi. The black wants to be attached to the white desperately. You see down here? It comes in just as quick as it can get to that white. It never leaves the white hardly at all. But it can't get through the Venturi. What do we want to charge a battery? White. That's the only thing you want. You don't want that black. But it's hard to get the black away from the white. That's why chargers heat up and everything as you charge them. This is strictly removing the black from the white. Now, this may get real hot. I don't know. This is just, you know, and again, I did the same research as Rod. I had the same tools here, the same, and it was almost nothing. Well, here it is right here. This is everything he did and everything I did was done with this. All right, and a couple of nails. He had two nails right here, and they were close enough together that the black was just pushed out of the way and the white could squirt through. And that was it. Now, of course, he had other things, but he said this was the best to use. And I did some too, but I just, you know, he was so good at it, I just didn't get involved too much. But he used the selfie side, and he would put it right up here and pick up right in front of it and everywhere else. There's nothing more than CMOS in there. CMOS is a receiver. All right, it doesn't interfere with any of this stuff. It has no interference whatsoever. It just picks up on the radiance and it turns it into a picture. It depends on how many pixels you have and the quality of the CMOS. And this particular phone, he says, is the best he ever had. And this is the Galaxy S3. This is from 2014. I believe that's when we started with this stuff. And I think this was when all of this stuff is from this phone. It's very incredible, but it is true. And you can see all the black particles. You see them everywhere. They want to get back to the white. And back here, they're going to get back. They're going to get it back because they're going to slow that white down and become part of it again. At this range right about here. So what if we had put the receiver right there? All right, don't forget, this is it right here. We got that squirting through. The black never gets through, only the white. That's all the thing. That's the only thing that goes in your battery is the white. But to get it off of the black is almost impossible. That's why, again, generators, chargers, all that stuff, they create a lot of heat, and you have to drive that thing somehow. This, we're not driving anything. It's forcing those particles to just slap through there with the white. I mean the black. The black will move the white, and I can prove this. The black forces the white. So if the white is all over here, the black is going to just slap it, and it'll squirt through here. It squirts through there. I see no reason whatsoever we can't pulsate it down into the battery. Pulse, 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 as this thing pulses the laser. How long the pulse lasts for, I don't know. What types of lasers? I would say a complete complement of all the different frequencies, and then have a bunch of different transition metals over here that will absorb all those frequencies. Because right now they're up to around 30% using the perovskites. That's not too bad, but because this thing here this should be off the charts amount of electrons. You don't get electrons separated easily. They're doing sunlight, and they're getting a little bit of separation because the sunlight will, it hits stuff and it goes into the solar cells, and it does get transitioned. It bounces in against other and forces the electrons to be pushed into conduction, and then into batteries and so forth. We're just squirting it through here, so letting it slap through, and it's going to pulse itself. I mean, if it works, it's so elegant, it's just unbelievable. I don't know what else to say. And if the thing, I think I showed you this, or maybe I didn't. If the thing that Rocco was talking about worked, we could put a Venturi this way, a Venturi this way, and hitting them in the center, and we might be able to double the voltage, because voltage is a very important part. Voltage is pressure. You got high voltages, really high voltage is 400 volts, 600 volts up in that area. We work with 120 volts in the United States for house voltage, and 220 for, which is basically double circuit to give you some really power. But this is basically the same thing, a double circuit. Maybe it works, maybe it won't. I have no idea. Somebody's got to look into this, and it's not going to be me. And Rod sort of moved away from this. I'm not sure why. I haven't had much contact with him, but he's the guy that did this, and I give him all the credit. If he didn't really know what he did, I contacted him, and he was so gracious. And he said, "I'll do whatever you want." And I said, "Okay, here's what it is." And we did all kinds of stuff for years. And you can only take that for so long. And I kept making them think. I kept making them think that sooner or later they're going to pay attention, and they never did. So that's my tale of woe for the day, Rodney. I don't know where you are, my brother, but thank you so much, my friend. And Rocco also has great accolades for you, brother. And you will be known for this. Because this is what it is. This is what it is what it is. And what it is cannot be denied much longer. They're trying, but I don't know why. Why they won't embrace this. Let's take a look at it. No. We have to come up with something else to show that the standard model is correct. The standard model is not correct. The nucleus is made up of 1,823 dipole, what I call electrons, in the proton, an 1824 and a neutron, and then you just keep adding more and more and more of them, And because it seems to be a zone of stability, 1823 is basically a zone of stability. There's enough magnetism there pushing both different directions that they're sort of stable. The proton wants one more, I would say, or one less, to become an even number. Even numbers are the most stable. So you usually have one or two stable states in each atom, and then you have a ton of isotopes, and all it is a few extra electrons are missing. All right, so you take some off, it's still the same item. You say some more off, you can take hundreds of them off, and they still say it's the same item. You could put hundreds extra on, and they still say it's the same element. But it's an isotope. All right, and there's only certain parts of these particles that are all supposedly the same particles that are stable, and that's the ones that have the exact right number of particles in them. They don't want to give any up, they don't want to take any on. All the rest want to give some up. If somebody comes along, the right guy comes along, I'll give you some of these. Or you might want to take some on if the right one comes along. All right, stability means you're in the middle where you don't want to give up and you don't want to take on. All right, and light is nothing more than these same particles. Everything's made out of the same particles. Light is just the smallest part of a proton and an atom of material. And actually the muon, which is the black, is the smallest part, and the white is also the smallest part, and these are the particles. Here they are right here. Wait a minute, hold on. Remember I told you the black pushes the white? In this one, Rod had it set up so that some of the black came through. It must have been just wide enough for some of the black to come through with the white. And you can see what is pushing that white is this black. That's what's pushing the white. The white isn't just out there for nothing. The white is being pushed ahead of the black. And it's concussing ahead because these move fast. But the black comes slow. That's why an atomic bomb, you see a and then a second or two later, the first thing you're seeing is the white shock you, and that's it, way out here. And then a little while later, the black comes and knocks the house down. All right, we might need to radically revamp our understanding of the fundamentals of physics. That's the particle nature of what the physics is really made of, and the universe itself. That's exactly correct. And this is what we're going to do right now. Okay, I'm not going to go into a big, deep explanation of what dark matter is, but it's a hypothetical form of matter. They basically know it exists and accounts for approximately 85% of the matter in the universe, but nobody can see it because it doesn't emit, it doesn't reflect, it doesn't absorb. All it does is carry. It's a carrier of the white particle. Let me show you what dark matter is right now. Okay, here is the point particles from Fermilab. These are the smallest particles they can find. That one there is a muon, and that is dark matter. And it has a little glowy haze around it. And then the red one is the puffy one. It can get big and small, and that's where all the energy is. That's simply a carrier, and this one wants to be attached to that one desperately. That's why electricity flows through to the ground. That is ground, just like the earth is ground. That's why it's gravity. It sucks everything down, because everything has electrons, which is half of basically everything. So this is the particle, and that is exactly the same particle, identical to the particle that we see in the experiments. You see it? That's it right there. There's the fixed particle, the black one with the glowy edge. This is right off of Don Lincoln's page from Fermilab, and that's that one with the glowy edge. And then there's the white one, which is just a glowy one. It's not really white. It's the color, and I can show you. This is red. All right. So this is a red photon, and that's a photon. Half of this would be what they call a gluon. All right. They're nothing more than little bar magnets. And when you get down to the point where you smash these to bits, you get fission and fusion, and you can actually break the white away from the black, and that's what happened right here. You see it? This is the Venturi. A Venturi accelerates and crushes. All right? These are fields. These particles are not just particles. They have fields around them, like basketballs. This thing here can be tiny and it can be huge. And when it's slamming through something like this right down here, its field gets huge. And now all of them coming through at the same time are fighting each other. That's what creates this. And not only that, it's tuned so perfectly that only the white can get through. The black is kept off, and that's the muon. That's a fixed particle. It never changes size. See the black? And the only reason we can see it, it's on top of the white. Normally it would always be behind the white. The black, my conception of a proton and a neutron and all molecules is that the core, deep inside, is where the dark matter is. And then all the white particles crush around that and form a crust. And that's what all these atoms are. They're not, in other words, hydrogen is not one proton. Hydrogen is 1,823 or so dipoles. And then one more that wants to get in. And it says, no, you can't get in here. We got plenty. We're all set to go. Stay away. You can stay this far away with 2 angstrom units, whatever it is. And that's what stability is. And all of these are in zones of stability. They are not, this is lithium, this is boron, this is carbon, whatever. No, this is 1,823 dipoles. This is 7,350. This could be 20,000. You know, think about all the isotopes that are in between every single one of these elements. There's hundreds of isotopes, but there's only a couple of spots that are pretty stable. That means they're at the exact amount of particles. Says, I don't want any more, I don't want to give any up. I'm not reactive. All right, but you have to have all kinds of reactivity in here, and that's what enzymes do, is break up these little molecules. Enzymes are the most important thing in life. Otherwise, you could never make life work with these. Anyway, that's what we're looking at here is fission and fusion. There's no other way to explain it. And these are the particles, and they show it saying electron neutrino and muon neutrino. Together they call it a dirac, which is two sides, a black and a white. And the electron turns into showers, and the muon stays black, just a black ball. It can't get through. All right, so Fermilab confirms it, CERN confirms it, everybody does. Lawrence Livermore, they all see the same particles. They just don't know what to make of them because they're starting with big, huge things that just decay. Well, let me show you what they decay into. All right, follow me through on this. They've got protons and neutrons, bam, and they just slam into a million bits and pieces. But there's only what was in here. Each one of those is a big ball like this. So they hit 2 balls like this together, and then you just get all kinds of stuff. Now, you're going to see the photons, which I showed you. These are the photons. You're going to see some of these are going to come out as light. Yes, absolutely. And then you're going to see other ones, which are the red, blue, and the green. The red, blue, and the green little particles come out. Then you're going to see other ones that aren't fully formed, which are the neutrinos. And then you're going to see X particles, which are big chunks like this. Because you've got big chunks hitting together, and they just splash. So all they're looking at is this particle zoo and trying to figure out what's going on. I can show you what's going on because we started with that right there. That comes out of the laser, that exact particle. Let me show it to you. You see that? You never see the particle here. You would never see it. We're starting to accelerate it here. This is the pulse red laser. It's concussing with all the gases and electrons and heat and all that that's in front of it as the wave goes forward. Now we're going to accelerate it. All right, don't forget that's just a normal wave. Now it accelerates. Look at how fast that thing is pulling itself right out of the wave, like a rocket ship. And as it does, it increases energy. And when it increases energy, it gets more and more brilliant. That's what energy is brilliance. It's illumination. It's glow. And that's energy like coming out of your ears. And it's happening because it's fields, which are big like this. The particle is tiny, like a grain of sand. The field's big. They have to force into everybody else's field. That's what causes violence. It's called the Casimir effect. When you slam things together, that's when you get energy. And that's what's happening. We're glowing, and at this point right here, the black separates from the white, and all we have is white here. And I don't see any reason whatsoever that we can't collect that white with transition metal solar collector type thing right here. And just squirt that white down. Because what happens is this is a pulse. Boom, 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 boom. So you get the black, which can't get through. But it pushes the white. And it's going to be bam, 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 just like a piston. Boom, boom, boom. Squirting this down into our batteries. Bam, 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 bam. Can I prove that the black pushes the white? Absolutely I can. You want to see it? Of course you do. And there's the black, which was normally attached to the white, but it came through the Venturi, and they started to get in the separation zone, and the black ends up just pushing the puffed up white ones. That's what, and they push and make a flutter in front of them of magnetic push to shove. The black is not magnetic. It's not magnetic. It just pushes. That's why when you have an atomic bomb go off, and you're stationed right out here, the bomb goes off here, which is this is an atomic, subatomic, nuclear bomb. It comes through here, explosion. What comes out? The first thing way out here, you see all that brilliant radiance, all the brilliant radiance out here, and then you keep watching at the back to ground zero. And you see ripple, 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 ripple. That's the black coming across, pushing the white in front of it. Now, if you were in a test house, as soon as this real dense white hit, that house just vaporizes. It doesn't even move it, because this has no impact, no weight. It's just pure energy. This has all the weight, the black. So when this hits the house just vaporizes. Then the black comes and knocks the house over. So they're two completely separated particles. And the white one magnetically flutters ahead of it. And if you listen very carefully, which I have, it's my friend sent me this, Rocco sent me a sound clip of a nuclear bomb blast, and they're watching. And you see the blast go off, and you hear, that's this, instantly, because that comes with the light. That's the light. Violent light. It really didn't move anything. It's just you could feel it. You could hear it. Then you could see rippling across the salt flat or whatever it was a shock wave. And then the black came. But before the black hit, the house burnt up, because this is the part that leads. So this is literally a subatomic nuclear bomb. And the energy coming out of here is in that nuclear range. Let me show you one more time. All right, I don't think there's any physicist that would disagree with me that increased radiation and increased glow and increased light is increase in energy. Here you have almost no light whatsoever. And the particle is moving, it's moving ahead forward. But all of a sudden it got accelerated because of the Venturi and turned really, really hot. And when it hit the Venturi, it exploded. This is a subatomic nuclear explosion. There's particles like this that are moving forward. They're all over the place, but you never see them. You can't see them because they're not concussing enough. This one you can see a little bit because it's being dragged forward. All right, so you can see this one just starting to glow. These are glowing like hell because they're being pushed back at. You see this? This is what they call reverse EMF. Whoops. Hold on one second. All right, you see that particle, that line right there? That's the reverse explosion. All right, you got them going forward too. These are the going forward ones. But this, look at that. That's just an incredible amount of energy. From here, shooting this forward to here and making this atomic explosion, we're on steroids. And I don't see any reason we can't harvest that white right there, just like with that little device I showed you. All right, let me go over my claims. I claim these are neutrinos, neutrino. These are photons, fully formed photons. Now, and this is red because it's coming from a red laser, and that's the speed of the spin. The spin determines the color. This is the green, same particle, identical particle, no difference whatsoever. Same neutrino types as their, but the green is much hotter, much more intense, and the blue is just out of control. Here's the blue coming through. It's coming through so fast it's almost straight, and then it starts to slow down. Light slows down, speeds up, no problem whatsoever. Now the blue, as you can see, when it first came through, it looked like one particle. But as you can see back over here, it is actually two particles. But it has to take time to slow down for us to actually see that. Now, I showed how the neutrinos form into photons. Well, the neutrinos, they're in two flavors. There's Majorna and Dirac. That is a Dirac. The Majorna has a flavor to it. Let me show you. Here they are right here. The Dirac is the black and the white. That makes a photon, two side by side. But here you're in the phase of moving between, you know, you're not quite dark and you're not quite white, that type of thing. It's in the mat, and it's starting to charge up. Let's put it that way. These are charging up neutrinos, and that's a fully charged neutrino. Let's go with that. All right, so this would be the Dirac neutrino, fully charged, black and white. They show it side by side, but it's really up and down this way. Trust me. These are the spin, and these are Bauer magnets, and it spins on its axis. That's why there's upspin and downspin. This is in what you call downspin because this charged particle is down. All right. Anyway. All right. These are the Dirac neutrinos, and when they're not charged and they're starting to charge, you saw it was sort of grayish looking. When they're really charged up, you can see the black and white really well. And that's what we can see very well. And then they split. They actually, fission is right here and fusion is here. There's no other way to see it. And the electron showers, which is this, is literally raw electricity. That's the only thing you want to put in your battery. But when you have to use a battery charger and so forth, you're pushing against other molecules. You're creating a lot of resistance to it. This is just automatic. It just happens because of the crushing of the fields. And we have another process, possibly. My friend Rocco has maybe got a way of hitting head-on photon beams and collecting the energy in the center, which would double the voltage, possibly. All of this is a little on the edge right at the moment, but this is from CERN and Fermilab. They just don't know how to find these because they're working with gigantic particles. Like this, they're hitting them all at once. So they get that big pile of debris, just like this. That's all they see. And the red ones are because they're way on the outside, the least held, so they sort of just flop around. The blue are right down on the core, and they take off. That's why you see different colors of light, is because of their different magnetic bind. All right, so if you got one that is right stuck to the core, I mean, to get it out of there, it's going to be blue. It's going to be blue or ultraviolet. It's going to be almost, it'll never come back. It's gone. Well, if there's one out here somewhere, it would take off and not have so much energy, have to pull it to get it off. And if you have one way out here, it just sort of bounces around. That's what the red is. All right, that's why you see these, they call these Higgs fields. Well, you want to see some Higgs fields? I'll show you some. Here's Higgs fields on steroids. This is the white particle. That's all it is white. That's all it is the white particle. All right, that's half of light. That's the energetic half of light. The other half is the weight. It pushes or carries. All right, these want to be back to the black, and that's what they're doing right now. They're hitting some black particles here, and then they're all going into spin. And let me show you something that really crazy happened. I think we had a reverse spinner, and it was an anti-particle. Hold on. All right, I don't know what exactly happened here, but coming through the Venturi, Rod was taking a picture coming at us, and the white spritz is here. There's nothing except white, and they're starting to hit the fields around and starting to come into the Higgs fields. But we're in the dead center of the white zone. You can see this particle here. That's spinning backwards, I believe. They're supposed to do a right-hand spin, I believe. Now you see all these little spritzes and how they're hitting these particles, and that's what happens. It comes through and it bangs into a black one, and they start spinning in these Higgs fields. Now, like I said, that's this one here, and one of this white is going backwards. Now, normally they just hit like this and they just all spin the same way. Well, that one spun backwards, and I believe this is that particle. So don't forget, here it is, spinning up here backwards, and it banged into one of these other fields and did a very, very strange thing. Right here, look at this. That's that backward spinner, I believe. Now, so instead of spinning this direction, this one is spinning correctly in this direction. This one's spinning correctly. This one's spinning backwards. So as it hits here, this one coming this way strips off a piece of it and spins it here and creates another little spinning disk. That is, I never expected any of this stuff, so almost nothing blows my mind anymore, but that sort of does. I believe this is an anti-disk. It's a reverse spinning disk. In other words, again, just to be sure you understand, this disk rotates in this direction. As it comes, they're all rotating. Now this one going backwards is rotating this way. Now as the two fields hit, the outside layer got spun off by the more powerful underlayer and grabbed it and started to twist it like it's going to uncoil that. Basically, it looks like to me. Because there's some kind of structure here and it created its own field, but it's not much of a field. And it's getting torn apart. Okay, I think I'll just leave it at this. You've seen the photons, which is the smallest particle of light, and the green ones and the red ones, they're exactly the same, and the blue is too, except the blue you really can't see. It's just too much, too fast. And they see them too. Right, there they are right there. And then they see all the other little particles. They see the green one, the red one, and the blue one, which is this three different colors that make up the neutrinos, and that's the speed of their spin. Now I'm sure there's other colors that are just don't spin exactly as the green and the blue and so forth, which is why you see yellow and you see orange and you see all those other colors. They're just not spinning the same way as the raw basic particles. I still haven't figured this out exactly, but it appears that the crystals that create the vibrations are the red, blue, and the green. Somehow those crystals create that specific vibration, that frequency that creates that color. Now when that color hits something and bounces back, you may not see it. You're not seeing it as whatever it is. You're seeing whatever color this represents as a bounce. So I'm sending the same light to that whole thing. The whole thing's getting the same light. Why is this green? That's blue and that's yellow. Why? It has to do with this molecule. This bumps back at a yellow frequency. This bumps back at a bluer frequency. The frequencies are frequencies of this. All right, they always thought they were waves. They're not waves. It looks like a wave. You look at it, it looks like a wave, but it's not a wave. It's a spinning particle. It spins, and when it's down here, it's blue. When it's about here, it's green. When it's down way out here, like it's red. And that just means the faster it's spinning, the more impact it has. The more impact it has, the more energy it has. That's why blue is much more energetic than the green or the red, because it's just spinning faster than hell. But they're all spinning. They all spin like this. And the reason you have the interference patterns are because they're magnetic particles. And they say, you stay away from me, you stay away from me. So they set up these lines of interference. All they are is repulsion of magnetic particles. It's not flapping waves like this. And it's still being taught that way. Very, very hard to understand why they can't look at this. And I'm hoping this fellow that I'm sending this video to will engage. I'd love to have that. And as far as I'm concerned, I'll engage with them and help and show everything that we have. And that's just a start. That is just the start, my friends. But if we knew that the particles that make up everything was this black one and this glowy one, which it is, that's what they are, and they make up these here. Every one of these is a dipole, just a little tiny bar magnet basically, and you get 1823 together, and they can literally push the black into the center and coat it with the white. So whenever you see anything, the white is there to bounce the other particle back. That's the Casimir effect. You bounce in, it bounces back. I call it push to shove. I push in, it shoves me back. Now, the light I send in could be a certain frequency. The light that comes back is not going to be exactly that same frequency. It might be if you had some really high optical mirror or something, but normally it's going to absorb something, and it's going to push back at a color. Some things absorb more than others, so you get different colors. It's basically as simple as that. It's really not all that hard to understand. Okay, as I said, I was doing this for another professor here that they're talking about visualizing the mysterious dance of quantum entanglement. And the whole idea of quantum entanglement is the same particle will find its same partner. That's the way I understand it. And I'm going to tell you right now, that's not going to happen. When they come apart, they just go on their own separate way. They'll find somebody else, but it won't be the one they left. You know what they say, if you can't be with the one you love, love the one you're with. And that's what happens here. When they break apart here, trust me, that ball isn't going to find the little white one and jump over back here. Absolutely not. They disentangle. And once they disentangle, they're on their own. So that's the only thing that I want to add to this entanglement situation. That's the way I see it. There's no way in the world these particles are going to find these same white particles. It's just not going to happen. And it also means that there's just got to be a ton of extra black ones laying around just waiting for some white ones to appear so they can mix up with them. That's the way I'm looking at it. Now don't forget, this is absolutely certain. We started with the muon and electron neutrinos attached together. When they hit here, it turned into the sterile muon and electron showers. That's an electron shower. What does an electron shower do as far as energy goes? Well, here's what it does right here. This is the physics of electron showers. They want to do all kinds of exotic stuff. Protons, hadrons, decaying, high energy flux neutrinos. We started with light, which is nothing more than neutrinos. We started with that. And that brings you up to when you at the neutrinos. We started with light, and we turned them into neutrinos, the muon and the electron neutrino. We just saw it. And that brings it up to 100 billion electron volts to a few trillion electron volts. That's staggering quantities of energy. And we did nothing whatsoever other than put it through a Venturi. We did nothing whatsoever. We just shot it right through a Venturi. There's got to be something that can be looked at here. All right? And these are the interference patterns, they call them, where they think they're flapping. It's not. That's a single slit. And these are the muons, which is dark matter. And then they recombine over here. And I think there must be a batch of extra dark ones laying around to get here, because I don't think they jumped over here to get to there. They don't do that. They push the white. And the white is they can't get through this slit. That's the key. That's the key. So somehow these black ones are showing up here. They got to be laying around. Now, one last thing. We're just experimenters. We're not any high-tech people. We don't have any high-tech equipment. Rod's nephew, Rod Warren, did all that light research, basically, the pictures and the experiments. Rod's nephew took this picture with his new cell phone. So, some kind of an app, I don't know what, but it's got all of the fields that surround all of these particles in space, planets and stars, and the moon doesn't have a field to speak of because it's not spinning, I believe. But anything that spins it turns into a dipole. They're all black and white, and they make a field. And here's some more he did. Well, maybe not. Oh yeah, here it is, right? Look at this. That's about as dipole as you can get. I think that's Venus. And you see the blue around the moon? Start thinking. You start thinking for yourself. What would cause that? What would cause all these fields? Why are they looking? Why? What's going on here? These are dipoles. Why is this blue? And why is this so orange? Right? There's a lot to think about once you start to understand. And now they're talking about, they just discovered, what do they call them? Gravity waves. Gravity waves. These are nothing more than magnetic fields. And they just discovered these. We've known about all of this stuff for many years now. And not to be able to talk to somebody is very disheartening. Now, again, this is done for a physicist who I am hoping will engage. All right, we'll find out if we have a friend here or not. So far, I have found very little friendship in the academic community. But if you look at the evidence I'm presenting, it's virtually impossible to just say, no, that's nothing, have a nice day. And that has happened to me by all the physicists so far. And don't forget now, I have a background in this. I was in the Army. I served at Nike Hercules missile sites in Alaska. I was in electronics my whole life. I understand all of these CMOS and all of that stuff, transistors and diodes and everything. And then I discovered other things within the last 10 years. And I went to the University of Geneva for particle physics. I engaged with them. They didn't give me any problem with this whatsoever. They were interested. So, but you know, it never leads anywhere because the big machines are where the money is. This is done with a couple of $100. Seriously, this was just, you know, just by some people in their garages and so forth. This is not high tech. You know, millions of dollars worth of investment for this. But it might give us free energy. It might give us other. Once you develop something, the concept, then that's just a start. Then you got to develop all the different products they can service, and you know, I don't see where anything is impossible with this kind of technology. If you can create over unity, which means you get more energy back than you put in, that's just free energy. Then you can do anything you want with it. And again, I got this thing here. Hold on. This stuff is so tiny that you could put literally hundreds, if not thousands, of these little devices inside of here collecting all this energy, and then have any kind of outlet you want. And then you just have regulators in here to make it 220, 110, AC, DC, 50 cycles, 60 cycles, whatever you want. You carry it around with something like this. In these war zones, disaster areas, and this would save the planet because there's going to be no expansion. That's the problem, is expansion. That's the problem. Is the greenhouse gases are expanding the envelope, and out at the surface of our ionosphere, where it crushes through space, which space is so saturated with particles, it's 3,000 degrees out there, something like that, 2,700 degrees to 3,700. It's thousands of degrees. Why? They have no explanation for that whatsoever, because they think space is a vacuum. Not at all. We are scrubbing our atmosphere through there, and that's what's creating all the turmoil on Earth and compressing and causing the huge amounts of rain and heat and hail. The hail is another, because it gets hot, then it gets cold, and then it gets warmer down here below. When it compresses, the cold zone in here, it still compresses, and it gets so compressed that big chunks of ice can come down. And I mean big. When I'm talking big, you wait to see if it gets much. The whole Earth is burning up right now. So we have to do something literally instantly. And this can be done literally instantly. It's that simple. But and we'd know one way or the other within a month. Even less. Can we put something through that Venturi and on the other side receive it, and there's more energy coming down here than we tapped off of here to run the laser? If that's the case, and I don't see any possibility that it won't be the case, we should easily be able to slap all that white stuff, which is that's the only thing that you put in your batteries is the white. You don't want the black. The black's just weight. The white has no weight. It just goes right in there. When you charge up your batteries, they don't change the weight hardly at all. They do a tiny bit, but not much. Almost nothing. For the energy you get is just staggering, but the weight, almost nothing. So if we can just keep slapping that down into the batteries, and out of a device like that, you could probably power your house or a car or who knows what. These electron showers, if you can get trillions of electron volts, and I don't see any reason why using different types of pulsation, different types of transition metal films to be the receiving devices, like solar panel type things, we should be able to do something like this. And that's where you bring in academia. Tweak it. Get the damn thing working. Otherwise, we're all going down with the ship, my friends. I guess that's my last word. I love you all.